Hi everyone, Ogar Plinkelton here, and this is the next edition of Existential Physics with Ogar Plinkelton. In this video, we're going to be exploring the magic of derivatives and differential calculus. And we're going to be doing a demonstration using this tiny little spring-loaded car, actually truck. And this truck is capable of producing constant acceleration. And we'll examine that and actually calculate its acceleration. And it maintains acceleration over a very short distance of about 30 inches. Anyway, I need to put some stuff on the board. I'll do that quickly. Okay, I'm going to quickly review some fundamental concepts that we need to know before we can talk further about differential calculus and first derivatives. And I'm going to go through this quickly because most of you are well aware of this, but this is the foundation you need before we can move on to the calculus. So let me remove my coat. So I'm going to talk about functions, the slope of a plot on the graph, and those are things that are fundamental to calculus. So a function is nothing more than two or more variables where the value of one variable depends on the value of the other. So we just use a real simple one. This is very easy. We're going to say y, one variable, is equal to another variable, x. And that can be written as a function of x equals x. Okay, so y equals x, the function is this right here. And I'm going to plot this on this little graph here, and y is going to be my vertical value, and x will be my horizontal value. So this is known as y versus x. X is the independent variable here, and y is depending on its value. Okay, we need to talk about the slope of a curve that we may put on here. And to do that, you need to remember that the definition of a straight line on a plot is y equals mx plus b. That's the definition of a straight line on this plot, or any plot. We have the y variable, the x variable, and m is the slope. We usually use m as our slope variable. B is the y-intercept. In other words, wherever our plot intersects the y-axis. Okay, I'm going to do a real simple one here. We'll do so our independent variable goes from 0 to 6. We're going to plot this function, y equals x. Well, if x is 1, or if x is 0, y is 0. X is 1, y is 1. 2, x is 3, y is 3. X is 4, y is 4. X is 5, y is 5. And lastly, x is 6, so y is 6. Okay? So I'm going to put these numbers, or these data points, at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Okay, so now I'm going to my meter stick here, plot this, just connect them. Okay. So the plot of this function, when x is equal 0 to 6, y is also then equal 0 to 6, and that's the plot of this function. Okay, now let's calculate its slope. Okay, slope is equal to the change in the y variable, delta stands for change, divided by the change in the x variable. So we're going to calculate the slope of that line. Well, if we just go from we'll do 0 to 1, the change in y is 1 minus 0, and the change in x, 1 minus 0. And therefore the slope is equal to 1. And this is so elementary, you can see that the slope anywhere on that line is going to be equal to 1, because y is equal to x. Okay? That's what you need to know. And, well, let's just do another slope of this plot. Let's do 6. Well, the change in y is 6 minus 0. And the change in x is 6 minus 0. Which again equals 2, 1. So the slope from here to here is 1, the slope from here to here is 1, and so forth. Slope here to here is 1. Anywhere on that line, the slope is going to be equal to 1 because it is a straight line. Now suppose we have a function that when plotted does not produce a straight line. And so let's change our function to x squared. Y equals x squared. The f of x equals that. Okay? All right, now I'm going to have to do some erasing and put some more stuff on the board, which I'll do very quickly. Okay, this is the important stuff. What I've put up here is a plot of this function, y equals x squared, f of x equals x squared. And you can see this is a curve, unlike the other plot that we did, which was a straight line. So how do we apply the slope and equation of a line to a curve? Well, we're going to be plotting, when we run our experiment with this little truck, we're going to be plotting the distance it travels versus the time. Okay, so let's, for argument's sake, assume that we took the data and we plotted it, and this is how the truck traveled. At 0, it hadn't traveled anything. After 1 second, it went 1 inch. After 2 seconds, it went 4, 3, 9, 4 seconds, 16 inches, and 5 seconds, 25 inches. So let's give our axes units. The y-axis is in inches, and the x-axis is in seconds. That means that our slope is going to have, you guessed it, units. And they're going to be in inches per second. And inches per second is a unit of speed. So that means the slope on this curve is going to give us the speed at which the car or the truck was traveling. Okay, now let's figure out how we can apply the line, equation of a line on this curve. Let me get my... So let's take a straight line between these 2 points. We'll do these two. Okay, if we take the slope of this line, our change in y is 16 minus 0. And that's in inches. And our change in x is 4 seconds. And that is equal to 4 inches per second. Well, that's the average speed between these 2 points. The cart was averaging 4 inches per second. But we want to know the instantaneous speed. We want to know what it is here, 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 every point on that curve. So, what are we going to do that? Well, let's say this is our delta x, which it is, 0 to 4. Okay, is everybody still with me? Okay. Well, let's make our delta x smaller. Let's go from 0 to 2 and make that our delta x. Okay, let's calculate that slope from here to here. I think you can see that delta x got smaller, that this slope is closer to the slope of this than at this point than this one was. And of course this is the change in y is 4. And the change in x is 2. And that gives us 2 inches per second. So the average speed from here, 0 to 2 seconds, is 2 inches per second. Okay, let's make our delta x even smaller. This is it. Delta x is just 2. And it's getting smaller. And now we're going to take the slope from here, and this is going to be our slope. And you can see that's even closer to the slope of this curve. So this is 1 second. Our change in y is 1 minus 0. Oops. Inches. Excuse me. yes, inches. And our change in x, delta x, is 1 second. And that equals 1 inch per second. That's the average speed of the car from here to here. Okay, now this is where it gets really fun. But if we make our delta x go to 0, basically get really, really small. All right, let's me do some work on the board real quick. Okay, our slope is equal to change in y and change to x. What if we take our delta x to 0, get it smaller and smaller and smaller? Well, if we do that, we take our function and we put in delta x, but we take it to 0, that becomes differential y over differential x, which is the first derivative of this. Okay, so let's work this out. Okay, I simply multiplied this through. This squared is x squared plus 2x delta x plus delta x squared minus x squared. And on the bottom, x minus x just leaves delta x. So now we can divide, well, we can simplify this. X squared minus x squared, that can go away. And then we can divide delta x into here and delta x into there. And if we do that, we have 2x, because that goes to 1, plus delta x squared, that just goes to delta x. And now we take the limit. As this goes to 0, this goes to 0, and we are left with 2x. That is the first derivative of this function. That gives us the instantaneous slope at every point on the curve. And the instantaneous slope of every point on this curve is the instantaneous speed of the cart if it traveled in this way. It's beautiful. Okay, and let's run the experiment. Ready, get set, go. Ready, get set, go. Now we'll run it in slow motion with the stopwatch in the frame so we can determine how far the truck went in the amount of time it took. After 0.14 seconds, the truck traveled half an inch. After 0.23 seconds, the truck traveled 1.625 inches. After 0.28 seconds, it traveled 2.5 inches. After 0.33 seconds, it traveled 3.625 inches. After 0.38 seconds, it traveled 4.563 inches. After 0.43 seconds, it traveled 5.375 inches. After 0.47 seconds, it traveled 6.688 inches. After 0.51 seconds, it traveled 8.188 inches. After 0.55 seconds, it traveled 9.875 inches. After 0.59 seconds, it traveled 10 3/4 inches. After 0.64 seconds, it traveled 12.5 inches. After 0.68 seconds, it traveled 14.375 inches. After 0.73 seconds, it traveled 15.625 inches. After 0.77 seconds, it traveled 17.625 inches. After 0.82 seconds, it traveled 20 inches. After 0.86 seconds, it traveled 22.375 inches. After 0.91 seconds, it traveled 23.875 inches. After 0.96 seconds, it traveled 26.25 inches. And after 1 second, it traveled 28.75 inches. All right, the experiment's over. Let's discuss the results. Let me clear the board. we're not going to do any hand plotting this time. I've employed the software Microsoft Excel. I entered the data points and it produced the plot for me. And what's nice about Excel is it will also determine the function of the curve that's been plotted. So this first plot that's up here is simply the distance the truck traveled versus time. It's simply those data points that I just illuminated in the video. And you can see it has the shape pretty much of that curve we did earlier. Okay, this next slide is the same plot, but this time overlaid it is the Excel generated function that it believes the data points are closest to, and you can see it overlaps pretty well. And up in the left-hand corner is the function, and you can see that. Okay, so that is the function of distance versus time, and if we take the first derivative of that, it's going to give us speed of the truck versus time. Okay, and now this plot is the speed versus time of the truck. It's simply, I took the first derivative of distance versus time and plotted it, and this is what I get. And you'll notice that is a straight line. And the next one then, next slide, is the same plot, again, this time with the Excel determination of what the function is of that line. And it's up there at the corner. Now, the first derivative of speed versus time is, you guessed it, acceleration. And so if we take the first derivative, which is 53.346, that means that the truck traveled at constant acceleration. And this next plot is acceleration versus time. And you can see that it's a constant. And the next one is the Excel determined value of that straight line of the function, and you can see simply y is equal to a constant, in this case 53.346, and that is inches per second square. All right, so that's it for this video. I hope you learned something. Until next time, take care.